Hey guys, welcome back to CS395. This is week 3. We're going to be talking about buffer overflows with shellcode and partial overwrites. So last week you guys talked to Nihal about making shellcode and compiling that and doing that with the purpose of running bin sh and giving us a shell. The reason why we care about that is because if you remember 2 weeks ago when I was giving you guys a problem to do, a buffer overflow problem to do, we had a get shell function that we were running by modifying the return address. Most programs aren't that generous, so we won't get a get shell function probably ever again, which is unfortunate, but we have ways of dealing with it, and that is by pushing our shellcode onto the stack ourselves, making our own get shell function essentially, and pointing the return address to the shellcode, and then the shellcode runs and gives us a shell. And I'll be teaching you guys how to do that today. Important note is that there are protections against this turned on by default in C programs. We have those disabled, of course, for these problems today. For this lecture, we won't be worrying about that. But because we're pushing our shellcode onto the stack and running it, usually the stack is not executable. This is called NX. The portion of the stack where we can write is labeled as non-executable, so nothing we put there can actually be executed. But today, it will be. So, how do we pull this off? It's very similar to what we were doing 2 weeks ago. We have our typical buffer overflow with the vulnerable buffer in the local variables section. We just want to smash the local variables in the base pointer, replace the return address with where we want it to go, except instead of pointing to someplace already in the program, we're going to point it to our own shellcode that we also push onto the stack. It's important to note that I have the shellcode here above the return address on the stack. If you have enough room down here in the local variables, you can put the shellcode here instead of junk and then point to that, and that'll save you some space. But you can't put it up here. We're going to be putting it up here today, but you do have that option. So to demo this, I have a program here for us. It's a simple buffer overflow again, just 200 bytes going into a buff array that is only 10 bytes. So we smash that, we smash the marker, and then everything above that we have 180 bytes to play with, which is more than enough room to fit our shellcode from last class. Also notable about this program here is that it prints the address of this variable right here on the stack, which is going to be very helpful to us to make our payload. So the whole key to this exploit is that we need to know the address of our shellcode. Other than that's the main thing that we need to make this happen. So to get that, we are lucky enough to have a marker give us its address on the stack. So to get the address of our shellcode from the address we have, which is marker, so let's just pretend that we have this. This is our address for marker right here. We know that marker is it has the base pointer, the return address to go through before it can get to the shellcode. So that's we have to the marker to smash that. We go through 4 bytes, and then another 8 bytes for the base pointer, and then another 8 bytes for the return address, which ends up being 4 plus 8 plus 8, so 4 plus 16 plus the address of marker gives us the address of our shellcode. So we can just map that out pretty easily. So then our final payload would look like 22 bytes of junk because we want to overflow buff, which is 10, overflow marker, which is 14, overflow base pointer, which is 22, and then everything after that will be our return address. So we have our 8-byte return address here that we modified earlier, and that will point to our shellcode, and then we'll just run the exploit. So hopefully that isn't too confusing. If it is, it won't be in just a second because I'm about to explain it to you guys. We're going to do a live demo, and hopefully it'll make sense then if you follow along. So let's get into that. Okay, so here we are in the Kali VM in the week 3 folder, and in the shellcode overflow folder as well. This is where the demo problem is. You can see I have a problem here for us, the same problem from the slides, and I have 2 solutions here. Because solving it in GDB is a little bit different from solving it on the command line, which is what CLI is. So first let me show you guys something. If you run vuln, it'll give us, it prints us the address of the marker, and that's nice. But if we run it again, you'll see that the address is actually different this time. And you run it again, you'll see that you actually get a different address. This is because I just turned on my VM for the first time today, and ASLR turns itself back on every time you reboot the computer. So to do this, ASLR is stack randomization, so that's what it does, is it randomizes these addresses on the stack, which is a bigger problem that we'll tackle later. So for today, we're just going to ignore that, and that's why we have this ASLR script for you guys. I'll just turn it off there. Cool. So yeah, that's something to worry about. So if you're having trouble, make sure that that is off. That should be the first thing you do before you start this problem. Then also worth noting is now if we run vuln, you can see that we will get the same address every single time. Yep. But if we're doing this in GDB, yeah, if we do GDB vuln and then just run it, you can see that we will get actually a different address here. This is not the same address as we got when we were running it from the command line. That's because GDB has its own way of addressing. It has its own like environment variables, so the stack addresses are going to be different from your command line, and there's nothing we can really do about that. So keep that in mind as well. If you make an exploit for the command line, it will be different than then it probably won't work in GDB. Okay, so now that that is out of the way, we can start our exploiting of this excellent little program that says hi to us. So we already talked about what we're going to do to solve this. So all we need to do is act out this plan. So we start. What do we need first? First, we need bytes of junk to push all the way up to the return address. So let's go here. The way we're going to write our own. This is kind of a spoiler. Before 2 weeks ago, when we did our first buffer overflow, I showed you guys how to use Python to write our payload to a file, and then we used that file. We used a file redirection to use that file as input to our vulnerable program, and that's how we injected our payload. That's fine. That still works here, but this process of what we're doing now is very prone to error. It's really easy to make mistakes. And having to open a file and then write to it and delete the file if it's wrong over and over again can be very tedious. So this is a more verbose, kind of slightly uglier way in my opinion, but it's a lot more helpful when you need to make quick changes. So what we're doing here is we're importing sys, and then we're using the function sys.standardout.buffer.write. And that's a mouthful, but basically all it is, you can think of it as just print, basically. What it does is it just writes whatever we put in here to the standard out of this program. So we can just write our payload here and then pipe it into vuln, and then that will do the same thing as the file redirection we did in the last class. So this kind of gives it away. It kind of ruins the surprise here with this autocomplete. It's pretty disappointing, but we'll just do this bit by bit. So everything in the quotes is run. Python 3-C, if you don't know, just lets you script Python from the command line. So if we run that, it'll print 22 A's, which is excellent. So that step one is done. We have 22 bytes of junk. My goodness, that's annoying. Now we want to get our address of our shellcode. So how do we do that again? We need to take our marker address and then add 4, 12, 20 to it, and that will give us the address of our shellcode. So run vuln. There's our address again. Now we need to add 20 to this. I don't feel like doing math in my head, so we're just going to do it in Python. Add 20. Beautiful, beautiful, beautiful. So this is the address of our shellcode. Oh, goodness. Sorry, the recording my screen and running this VPN, or this VM, makes selecting stuff really hard for some reason. Okay, anyway, so we have that. Now we can go back to our, just hit up, use the up arrow on your keyboard, and that'll bring you back to previous commands. So we want to do this plus B. Oh, and the reason why we're using B in front of these strings, by the way, is because we want to send, this is a Python 3 thing. You use that to send bytes instead of just, ASCII characters. And actually, we want to, I'll just paste the address here for reference because we need to write it backwards because x64 is a little Indian. So E0, FF, FF, and that's 3, and then X7F. Okay, also one thing to look out for that had me stumped for a while is marker was printed, and it gave us this nice address, but if you actually count it, this is only 6 bytes, and we know, because we're computer science geniuses, that 64-bit pointers are supposed to be 8 bits. So what the heck is going on here? It's there's actually leading zeros, 2 null bytes right back here that it's just not showing you because it doesn't actually affect the numerical value. But we need to include those because those 2 bytes, if we just have a 6-byte address here, you can see that there'll be 2 bytes left over in the return address slot, and part of our shell code will be considered part of the return address. We don't want that. So we have to add our own little 2 null bytes here. Wonderful. Let's try printing this now, just to make sure everything's still working. Okay, cool. Obviously these bytes just are random and can't be represented by ASCII characters on the terminal. So now what we want is our shellcode. This is exactly what we did last class with Nihal. So I have all the, we're going to use the shellcode. We're doing source here, yep. We're going to be using, I'm using bestshell .asim from last class, and I went through the trouble of converting it to just /x terminated bytes, so that way we can just easily copy and paste into our exploit. So that saves you guys some trouble. But we want to go to shellcode. What was it called? Overflow. Yeah, this is where our problem is. So then we want to get back to our exploit here. Yep. So then we want to add another string just to keep it separate. And then paste that. And there we go. This is our exploit, I think. So all we have to do now is pipe that into Vuln, and hopefully this will give us a shell. Wow, it does. Okay, I never get this right on the first try. Yeah, so obviously I didn't use GDB to do this. You don't really need to because this is very calculated, but it helps. So I'll show you guys how to do that in a second. But yeah, so we have our shell because we ran our shell code. We had our return address point to our shell code, and that ran. Runs the whole thing, just travels up, and that is what gave us our bin.sh in a program. Oh boy. In a program with no get shell function. So now the rules are the cuffs are off. Now we're hitting heavy. This is a seemingly pretty innocuous, non-threatening program, and now we have control of the dude's computer. So you can see how powerful this stuff can get. And you can do anything with shellcode. We have complete control of this guy's computer now. But I'll show you guys how to do this in GDB because it is slightly different, and there are some things you need to look out for. Okay, so here we are in GDB, and I wanted to show you guys the differences between doing this on the command line and doing it here. We didn't use GDB for this one just because we have the luxury of being able to do it like really calculated. We can just math it out from the beginning, so we don't really need GDB for a program like this. But there are some things I want to show you. So the first thing I want to show you is a program called Checksec, and this is a separate program, but it comes with GEF, the GDB plugin we have. And what it does is it shows you nothing. Okay, it looks like I'm missing. Yeah, okay, there we go. So Checksec will show you the protections that are enabled on the binary that you have loaded into GDB. So you can see we have canaries turned off, we have NX turned off. This is what I was talking about at the beginning of the lecture. If NX is on, then the stack is not executable. So we have our part of this exploit is we have our return address pointing to shellcode, and then it runs the shellcode. If NX is on, if you point the return address to shellcode, NX will say, yeah, no, you can't run that, and then it'll just segfault. But we have that off for now. We won't worry about this. We don't need to worry about any of this right now. But in the future, when we start teaching you guys about these mitigations and how to get around them, we'll start throwing these at you, and you'll need to know which ones are on and off. So Checksec will be your helpful tool there. And then I think regular GDB has this, but disassemble main is useful. It disassemble any function. Shows you, of course, it's the disassembly for stuff. Lets you know, like stack variables and things. Just useful to look at disassembly sometimes. But what I didn't know, I just found this out recently. Check this out. You can actually set breakpoints using these little offsets here. So if we want to, very often we want to set a breakpoint right before the return instruction. So if we do a main like 105, bam, we have our breakpoint right there. I didn't know that. Maybe that was common knowledge, but I thought that was really cool. So anyway, let's get back to what we're actually supposed to be doing. If we take our, I said that exploiting it is very different. I'm going to cheat here. I'm going to pull our command line solution up. Yeah. So running this in GDB is different than running it on the command line. So we're going to have to make some changes to our payload here to get this to work out. So first thing you want to get rid of is this /vol. You know, that's not how you run the program in GDB. So we'll just get rid of that. Next, we want to use our Python 3 script here, our Python 3-C, as input for GDB. And if you remember, we use R, as just the letter R to run. But we need to use a bash command substitution, which is basically just surround the whole command in parentheses, and then have the greater than symbol right next to it, and that'll let us run the command and then use the output for GDB. And it's really annoying that you have to scroll up through this whole thing just to do this, but and we'll have I'll teach you guys a better way of doing this. We'll be scripting our exploits. 2 weeks from now, I'll be teaching you guys how to do that, and then everyone's lives will collectively get 10 times easier because that is so helpful. I don't know if I've already talked about that. But anyway, we're taking R, we're using the input from our Python script, and so that'll run it. But if you remember, I talked earlier about how GDB has different addresses, different stack addresses. So this is not the same as what we have. Yeah, I know, my battery's charging. It's not the same as what we have here for our command line. So we need to take this number, our marker address, and add 20 to it like we did before. So we'll just copy that, and I'm going to cheat and go to my actual computer. And then we'll do the hex of this plus 20, and then that'll give us the address we actually want. So we'll just go back down. So that's our actual address, and then we want to pull back up the, come on. Oh no, I quit GDB, I didn't mean to do that. Darn, let's GDB volm. That was just straight muscle memory, me quitting GDB, I did not mean to do that. Yeah, so we'll just pull this back up, easy peasy. And I'll, before we do that actually, let's just put that here so I can read it. Then we just want to change those 2 bytes of our return address, the first 2 there, because they're the only ones that are different. I can't wait to not have to do all the scrolling. And here we go. So we want to replace this with DF, and this with 80. And now we run this and it should work. Now, oh wow, look at that. We need to reset our breakpoints. So this gave us a shell. So this works now, which is cool. But let me prove to you that this is actually running our shell code. So let's set another breakpoint. Let's do our handy dandy disassemble main. Excuse me. No main in current contacts. What is going on? Do we have? Okay, I don't know what's happening. Yeah, so we'll do b star main plus 105. We'll actually run it. No, we don't want to run it. We want to run it with our with our shellcode here. Now here at the return address. So the return address return instruction pops the address off the top of the stack and then runs to execute it. So usually you remember this will put us at it'll run like libc start main or whatever. But here it's pointing us to some random looking data on the stack so if we run that, it'll jump us to, this is actually our shellcode now. And it'll run through, run each of our shellcode instructions individually. And this will result in us getting a shell. Now, this doesn't work. Actually, in GDB, you can see it executes bin dash and then freaks out on us. So, but yeah, that's all I wanted to show you guys how it is different to use GDB like this in the future. So now we'll get back to the main lecture. Yeah, so that's using buffer overflows to run shellcode. I urge you guys to do that on your own and try it yourself using my my exploits that I saved there, my CLI solution and my GDB solution as examples. If you try to run those yourself, they won't work for you because I can guarantee you that our addresses will be different, our stack addresses. And even if you reboot your computer, I think it might break your solves. Like if I ran my CLI solution again, I think it wouldn't work because I think stack addresses might change after a reboot. Anyway, we're moving on now. Yeah, do those yourself. This stuff is actually very difficult. It's very easy to get something wrong. It's very precise. There's no room for error, really. And if you get like a seg fault, it's hard to tell what's exactly wrong. So you have to make sure that you're doing everything very careful, that you're crafting every part of your payload exactly the way it needs to be. I just wrote down some important notes for you guys. We did this with ASL turned off, but I actually I think this might be possible with it on. I might throw that at you guys later. But yeah, just food for thought. The marker address is different when you run in GDB, and I just have wrote down the different ways of running this in the command line versus on GDB, and some stuff about the pipe if you don't know much about the Linux command line. So now we're going to briefly just touch on the idea of a NOP sled. This isn't very relevant now. This is mostly an ASLR mitigation technique. But the general idea is if you want to run shellcode and inject shellcode, and you have control of the return address, and you want to point your return address to your shellcode, but you don't know exactly where your shellcode is. Like before, we just were able to math out our shellcode address, but you probably won't get a free marker address like we did. So, but you might have an idea of where it is. Like the first few, you can see, ooh, not that way. If you had like the first like 7 bytes, and then it was just down to this like 1C, and you didn't know what that should be, you can just prepend your shellcode with a bunch of NOPs, which is hex 90, which is that's no operation instruction in x86 and x64 architecture and Intel. So basically, what happens is you just guess. You say, okay, I think my shellcode's here, and then if you hit a NOP, it'll just continue to NOP. It'll go NOP, 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 and then till it hits your shellcode, and then it'll run your shellcode. So basically, this just increases the odds of you hitting your shellcode with the return address if you're in a situation where you need to guess or brute force your shellcode address, which we'll probably have a challenge for you guys that uses this later. So not using this today, but just keep this in mind. Okay, so this is our last topic for today, and it's called the off by one overflow, which is a really common programming mistake using arrays that that I've definitely made. I'm sure all of us have made it at some point. But basically, it's just any code, doesn't have to be an array, I guess, that is executed one more time than it's supposed to, and that leads to undefined behavior. So we have a for loop here, for example, that copies 15 bytes from string 2 and puts it into string 1. So string 1 can only hold 15 bytes. But because this is a less than or equal to rather than just a less than, it actually ends up copying 16 bytes into this 15-byte buffer, which of course makes it overflow and have 1 byte extra smashed through the 300 integer here. So that will change this value. So after this for loop is executed, this will no longer be equal to 300, and that's the objective of this program right here, is to try to figure out what 300 is equal to after this loop is run. So let's try to do just that. If you run the program and guess 300, you're going to be wrong because, as we just said before, we know that the last byte of 300 gets changed. So here's 300 in decimal is equal to this in binary. And it's actually represented, this is 9 bits right here. And we know a byte is the last 8 bits, which is what I have underlined. And this is what gets changed by that 16th byte of string 2. So to figure out what the 16th byte is of string 2, we can just count. Just go like 1, 2, 3, 4, and then we know that this is the 16th byte. So these 8 bytes get replaced by whatever whatever a exclamation point is in ASCII, because that's that overflows into here. So to figure that out, you can just Google it. Is probably the easiest way. What I have here is type in man ASCII. Let me just do that again. Man ASCII. You can get the ASCII table, which will show you all of the decimal and hex values of characters. So that's what I have. If you look up the exclamation point entry, you can see it's 33 in decimal. So using that, we can figure out what this value is now after the for loop. So after the program runs, we know that these last 8 bits are replaced by the exclamation point. And since the exclamation point is 33 in base 10, we convert that to binary. That becomes this. And then we just add in the leading zeros it's missing. And then we figure out that this is what 300 actually becomes after we run the program. And it's 289. So if we run it, /vuln with 289, you can see you win. So this is a simple topic, but it can be pretty powerful. Right here, this is just a silly, we just changed this one variable here. But a programming mistake like this can actually be fatal. Sometimes this is really dangerous because you might not even notice that this is happening. If you don't use 300 again after this, you won't know that it's changed, and this can actually be used to redirect program flow. Like, what if 300 wasn't here? What if its string just went up and then this copied a 16th byte to the base pointer? That would cause a crash, or if it didn't cause a crash, then a hacker could potentially use that to redirect program flow. But that's all we're going to talk about this today. I think that's that's our last slide. So now we're just going to get down to the homework. This is your guys' first assignment. So I have it here for you in just the, I think it's just in the homework folder right now. This might not be called homework by the time you guys get it, but it's homework 1.c, and you guys won't have the solution, but you will have to make your own solution. So your goal is to get a shell, or I think, here, let's see if I can open this up. Hopefully this is the same assignment you get. Let me see. Yeah, goal is to run a get shell and get a good job printed. Then you can do whatever you want. I have some things to include. You're going to have to submit a write-up, which is basically just you telling us, me and Neil, how you did what you did, like why you did the things you did. Oh, the first thing I did was figure out how far the distance is between, my vulnerable buffer and the return address. And then I did this and I did that. So write all that stuff down. I know that this stuff can be really hard to pick up. So whatever you try, even if it doesn't work, write that down, especially if you can't end up actually solving the binary and getting a shell. If you include everything you tried and you show effort, then we can give you partial credit for that. And creative, we also love to see creative solutions. There's no protections on this binary, so you can really go ham with it and do whatever you want. There's a lot of different ways to solve it, so we'd love to see some creativity there, because binary exploitation is more of an art than a science. That might not be necessarily true, but there's a lot you can do with it. But that's all I have for you guys today. Thank you again for watching, and I'll see you in a couple weeks.